Hello, everyone. I'm Kevin Gifford. I'm faculty within the TCP program. Today, we're going to have our Engineering Design Spring Expo, also called our TCP Spring Colloquium. We have 11 really nice projects. I will have a couple words to say about the projects and how this course was ran, with an emphasis on engineering design. But before I do that, I want to introduce everybody to our new director, Dan Massey, Professor Dan Massey, and he'll have a couple words about our new program. Cool. Thanks, Dan.
All right, thank you, Kevin. Okay, so just a couple quick announcements. We've got a lot of exciting stuff coming up in the next, just month or so. So first, for most of the teams here, in just around 2 weeks or so, you're hopefully all going to be graduating, and congratulations, moving on to the, out into the next step in your careers. So this is great. This is building on the Interdisciplinary Telecom program, which is the program that these students came into. And it was established in 1971 with its focus on really being interdisciplinary, right? It was a combination of the technology and the policy. Dale Hatfield, one of our founders and one of our lead sponsors, used to say, we get the technology that might get you your first job, and the policy, the management, and the strategy that's going to let you move up in your career and get you your second job and beyond. So that's what the program's been about. March 4th, we went through a major rebranding of the program. So we have changed the name from the ITP program to the Technology, Cybersecurity, and Policy program, as you see up scattered about here. So we are now TCP. We are staying true to those same roots, which is if you do anything in network engineering, anything in wireless networks, anything in cybersecurity, if all you know is the tech, you're still going to find a job, just because, frankly, we are so desperate for people. In cybersecurity, we have a 1.8 million workforce shortage projected by 2022. So I won't go as far as saying, you're going to have a hard time finding a job. You aren't. You're going to have an easy time finding a job. But to move up, to become the project manager, to become the CTO, to become the founder of your startup, to become the CEO of the company. By the way, there's a great study from Harvard Business Review where a lot of the successful CEOs of Fortune 500 companies actually have engineering degrees rather than business degrees. Right, so that's the kind of thing we're aiming for. Cybersecurity very much fits that. Network engineering, wireless, policy all fit into that world. That's kind of where the project, that's where the program is headed. We've got a great set of soon-to-be alumni that will, in mid-May, you will officially be alumni of the program, and congratulations to everybody. We've got a great set of industry partners who've been working on the capstone projects. I can't say enough about all the work that Professor Gifford has put into really driving this forward, to engaging with the teams, and we expect to only get bigger and better from here on out. Amazing projects out there, and I think that's sort of the big picture on the program. I'll just take, if there's like one or two quick questions on sort of big program directions. If not, I'm going to get on to the exciting stuff, which is really the work here. So anything? Looks like we're good. We want to get to the exciting stuff. So let me hand it over to the real master of ceremonies here. And Kevin, congratulations on a great set of students and great set of capstone projects. And let's see what we got.
Thanks, Dan. I very much appreciate the kind words. You guys, I have one slide here, and then we're going to get to the project. So I've been the graduate projects course coordinator, and I want to emphasize I've had really great support. Couldn't do it without our academic advisors of Dr. Levi Perigo, Jose Santos, and Dr. David Reed. So thanks to our academic advisors. I want to make a special acknowledgement to Aerospace Corp and to Equinix, who both sponsored two of our projects this year. We do have mechanisms on the web for corporations to sponsor these graduate projects. Typically, you guys, I've seen this work out great. The students love working with the company. They love the company mentorship. You often, with a corporation, you have a very focused problem. So that's nice from an engineering design perspective to have a problem with the specific requirements. And just in general, you guys, one of the slides we have the students do at the end of the year is, compute how much man hours and what the cost of your project would have been in industry, assuming you make $41 an hour, okay? And it always comes out to be around 200, 250K. So you get a lot of effort from the students, and they do a quality job. So sponsoring projects in the future, if anyone is interested, please feel free to reach out to me at any time. And again, a special thanks to Equinix and Aerospace Corp. All right, guys, my one slide is this. So in this course, I really focus on engineering design. I think it's one of the critical skills an engineer to have, to know how to step through the design process. So, there's a lot to it, from the project definition to conceptualization to doing a critical design review. And then, stepping into testing in the spring, where you do your testing review and your final project review. I will tell you, as an engineer, what I really focus on, and the students know this, is certainly you got to define the project, right? You got to scope it correctly. That's lesson number one. But a couple of the big critical items of engineering design are doing engineering design trade-offs of all the potential solutions to address the problem. You're not going to see all that, what I consider critical engineering. You're not going to see all the engineering design trade-offs, because these are 10-minute presentations. And also, the other big thing besides engineering design trade-offs is test readiness, right? Even if a project, has problems, you can really tell the dedication of the students if they write a very good test plan. Then hopefully they have time to execute it. So on a personal level, you guys, I really emphasize the entire engineering design process, but the key components of engineering design trade matrices and also the testing plans, you're not going to see, right? Because you're going to see the results. So I just wanted to put that caveat out there. We've got a great team, or a great group of students. I know this is an eye chart. Don't even try and read it. But I wanted to give you that background. So with that, we'll get started. Team one, why don't you come on up, and I'll hand the microphone over to you. We'll see how fast this syncs. Hopefully it's just going to be, oh, that was pretty quick. All right, team number one.
Hi, everyone. My name is Sandeep. On behalf of my team, Karthik Bandari, Mansa Suresh, Rodney Manuel, Siddharth Shah, and Soumya Sundaram, guided by Dr. Levi Perigo, Dr. Kevin Gifford, and Devang Gedia, are here to present our project, Data Analytics for Service Provider Networks. So this is the agenda for today. I don't want to go through it. Okay. So why am I here today? On November 11, 2018, Google faced a major outage that resulted in major packet drops as well as congestion. Why did it happen? It's because some autonomous system in the internet originated some internet prefixes which does not belong to it. I'm here to, our project is about how we can correct that route leak and in an automated fashion in less than 10 minutes. So what is the problem? The problem is about the route leaks and the route leaks originate because improper network prefixes are propagated and preferred in the internet. This is because BGP, Border Gateway Protocol, that is used in the internet is not designed with security in mind. How can a route leak occur? It can occur due to two reasons. One, either due to misconfiguration, as it happened in the case of Google, or a prefix hijack, where a malicious autonomous system, where a person sitting in an autonomous system can try to get the packets just to snoop it or use it for other purposes. So our project is about how to reduce the impact of this route leak by instantaneous detection and correction. What is the current solution that is there in the internet today? The routing tables are analyzed manually, and the originator of the route leak is analyzed and then detected and corrected. It takes around 2 to 3 days to do this. But our solution does it in an automated fashion, where it is running continuously to detect the route leak. As soon as it detects the route leak, it corrects it in less than 10 minutes. So these are our 3 levels of success. The first level of success is getting the test environment where we have an ISP kind of environment with all the routers, like where we have 3 autonomous systems and server that is running to get the data from the routers and stuff like that. Our level 2 is going to be detection of the route leak and alerting the autonomous system that is originating the route leak, as well as the enterprise where the code is running. Third level is the main part where we correct the route leak after getting the permission from the NOC team, so that we make sure that we are not doing something like a false positive. This is a concept of operations diagram. We have all the routers running. The data from the routers is collected from through a server, and the data by using a container named Kafka, which is nothing but like an application which allows multiple applications to fetch the data from. And the database application is going to get the data from the server, and the code, that is the algorithm that we use, is going to get the data from the database, and it is going to detect whether there is a route leak. If there is a route leak, it is going to send the exact route leak to the NOC team to check whether it is really a route leak. If the NOC team says, yeah, it is a route leak, then we go ahead and add the corrective solution back to the routers so the route leak is corrected. This is just the screenshots which show like our solution. What you need to know from here is what are the parameters that we use for detecting a route leak, which is going to be origin AS, timestamp, whether if the route leak has originated recently, then we have more chances to say that it's a route leak exactly. Also, we have a dashboard which keeps track of the prefixes to which ASs they belong, as well as the timestamp when they originated. If it detects a route leak, we are going to send an email which might look like this with a link. When the user clicks the link, they get a web page similar to this where they can choose, yeah, it's a route leak, yes, go ahead. If they choose an yes, we are going to add some prefix list back to the router so that the route leak gets corrected. So this is going to be our performance results graph where we show how much time it takes, where we break down the time it takes to correct the route leak. For detecting a route leak, the average is around 3 minutes because our algorithm is running every 5 minutes from the data that is pulled from the routers. Then we have given the human time as 5 minutes, like for confirming whether it's a route leak, that the yes or no question that I showed in the previous picture. After the user says, yeah, it's a route leak, the correction code runs in less than a minute. If you see in the previous image, if you can see, the code just takes around 17 seconds to run, so it is pretty fast. So the overall time that is taken to detect and correct the route leak is less than 10 minutes. So this is a performance result as well as a case study of the Google route leak that took place. The Google's, let us assume that Google is originated here. It was connected to an autonomous system named Main1. Main1 was the one which started the route leak. It advertised some prefixes which does not belong to it, but it belonged to Google. When it did that, the traffic, which usually just takes one hop from here, let's assume this is from Russia, the traffic that goes directly from Russia to Google took a different path, where there are multiple hops here. This route leak took around 74 minutes exactly to correct it. It started at 21:13 UTC, and it was corrected at 22:27 UTC. But what if our solution was there in place in China Telecom? Let us assume we are implementing our solution in China Telecom. As soon as Main1 originated some wrong routes, China Telecom, when it receives the route, it was around 212 routes that was wrongly originated. When it receives the route, our application takes 3 minutes to detect, 5 minutes to confirm with the user, and 1 minute to correct it. As soon as the route leak is corrected, it is no longer propagated. So the path remains the same. It just takes 10 minutes to correct it, whereas it took around 74 minutes with some major packet drops taking place in the internet. So this is how our solution is better. So finally, why our solution? Because we use open source platforms. all the containers that we use, either it be OpenBMP container or PostgreSQL database container or Kafka, all of them are open source. There is no money involved in that. Also, this solution can be deployed in a legacy infrastructure, as well as we can tune it to work in a software-defined networking infrastructure. This solution, so there are other solutions there in the world today, like Thousand Eyes and others, which only detect the route leak as of now, but we have a solution which can correct the route leak in the enterprise where the code is running and prevent it from propagating further. This is one major step, because all of the solutions that are there in the internet today just detect it and they do no other steps further. So what is our future work? Our solution, whatever we are tested right now, is just in the laboratory with 3 autonomous systems running. But there are multiple constraints when it comes to running this solution in the industry. We have to take all of those constraints into place before we actually implement it in the real world. As well as, another thing that we wanted to point out was the correction that we implement right now is only for the enterprise where the code is running. We can't correct it in the autonomous system where we feel is a hijacked one. We can just send an alert, an automated email to inform them, yeah, you're doing a route leak, try to correct it. But in the future, we can have some kind of global dashboard, something like which is being worked on right now, like an RPKI, where we correct it in the global scale. So these are our main future works. So the conclusion. So we focused on improving one performance metric, latency, from 74 minutes to less than 10 minutes. We learned a great deal about BGP metrics, as well as the route leaks and the kind of impact a route leak can have in the internet. We have tried to keep the solution as simple as possible. Thank you.
All right, if you're interested in more on BGP route leaks and automatic mitigation, please see Team 1 poster session outside. Let me pop open. Team 2, please come on down. Yeah. So here we go.
Thank you.
Yeah.
Good afternoon. We're Team 2, and we'll be presenting our project, a cloud lab infrastructure. The team members are Abhishek, Vishal, Abhinav, and myself, Apurv. Our academic advisor and customer is Professor Jose Santos. So in this presentation, we'll be presenting the need, what is the need of our project, what are the objectives, what is the engineering behind it, what results did we garner from the engineering, what is the cost related with the project, and finally some key takeaways. So currently for working on networking topologies and networking technologies, industry professionals and students have 2 ways. They can either work on a dedicated network hardware like our Telecom lab, or they can work on a network simulation software like graphical networks simulator software, which is GNS3. The goal of our project is to provide a software as a solution service, which is basically providing a cloud-based service of centralized network simulation software. We're using GNS3 as our main network simulation software. So in this slide, we've tried to map the challenges of the problems that are related with the previous stated 2 approaches, which is having a dedicated hardware and a network simulation software which runs on the computer itself, on the local machine. So our solution, first of all, provides, it helps us to check the infrastructure scalability problems, which is basically as the number of users increase, the requirement for devices increases. Our solution provides virtual devices on the go. Second is the need of physical presence in the infrastructure lab. So our solution being on a cloud, we provide internet-based solution and hence increase outreach. Moving further, we talk about problems related to network simulation software, which is if you run a network simulation software on your local machine, as your topology gets complex, the requirement for CPU and memory resources increases drastically. So we've tried to decouple and we've offloaded the requirements of CPU and memory onto our remote servers. Finally, coming on to the capital and operational expenditure costs related with infrastructure and local PCs, we've tried to offload it to our remote servers. So what we're trying to do here is we're trying to reduce the barriers to entry for students and professionals who try to work on networking topologies and technologies. Moving on, so we've divided our project objectives into two parts. The primary is decoupling the memory and CPU resources of the network simulation software on a local machine onto the remote server. Then we need to scale the service as number of users increase. We need to provision more devices for them. We need to provision a server environment local to that user. And finally, the secondary part is automating the entire service. We need to automate the service to make it resilient, make it smart, so that we can include features like snapshot service, user retention, provisioning of resources on the go, and cleaning up of idle resources. So let's come on to a functional block diagram. Our project has 5 basic blocks. The first is the user who requests the service. Second is the authentication mechanism, which differentiates the user as well as authenticates the user. Third is our blade service on which the service is running. A network attached storage in which all the user directories, configurations, topologies will be saved. And finally, the service itself, the software which runs the service. But that was on a high level. Looking into deep on the engineering point. So when the user request comes in, it hits our internet router, which resides in the lab itself, which is connected to a top-of-the-rack switch. The top-of-the-rack switch is then further connected to a blade server. It's the central blade server on which the Docker Swarm manager runs, as well as we just require one public IP so that the user sees that, okay, the service is working on this public IP and connect directly to it. So the user can connect to the service in 2 ways. The first is either VPNing into the CU Boulder network or by residing in the network itself. Another major part is that the top-of-the-rack switch connects all the compute nodes. That is not just the Docker Swarm manager, as well all the compute nodes on which the service will run, as well as the network attached storage. Moving further, so the manager is our most critical component because the central blade server or the manager itself is provisioning all the resources, it's cleaning up all the resources, it's actually spinning up a container as in when you request a service, and it's also responsible for load balancing and routing the request internally. So basically, our manager has 2 connections to the top of the rack switch. One is the public IP connection, and the second is the internal routing connection. We have automated all of this, and all of this is done using Python scripts so that no manual work is required by the manager. The rest of the slides will be taken up by everyone.
Thanks, Apoorv. Moving on to test results, we divided our test cases into 3 broad categories. I'll be going over the results of these categories. So first and foremost, we wanted to decouple the network simulation software itself, and we wanted to see whether the CPU and memory resources can be offloaded to a remote end from the client's local machine. So that's what you see in the snapshot here. The client could connect to a remote server, and the processor and the simulation software would work as it would work on the local machine. Next comes the scalability. So that was on a single server. Next, we incorporated Docker Swarm to have a complete view of the server farm and scale the service as and when user request comes. And not only that, but also load balance all the requests to all the servers which are running inside the server farm. Then comes the intelligence, resilience, and automation. So when we tested everything manually, we were good to go for automation. And right from the user request, capturing it, creating the user container, the GNS environment, fetching user files from previous sessions, and cleaning up idle resources when the session goes idle. All of that is done via automated script, which is running on the Docker manager itself. So once the user is authenticated in our service, all of that happens in the background, and then the user can access and create as many topologies with as many nodes as it wants to. So the resources will be provisioned on the go. I'd like to recap here that the primary goal was to offload the CPU utilization from the user's end to a remote server farm. And we tested that. We tested the topology from 2 perspectives. The snapshot above is showing you the CPU utilization when we run the topology and implement same protocols and perform same operations on the local machine when GNS3 is running on the local machine itself. And the snapshot below it is the CPU utilization when we use our service to do so. So you'd see there's a significant reduction in CPU utilization, and hence it gives the user to go for low resource or low compute power PCs and save cost on there. Moving on to the project cost, all of the equipment that we used for our project was in-house Telecom lab equipment. The couple of Dell servers, the Lenovo-based network attached storage, a Cisco switch, which was used as a top-of-the-rack switch, and Docker, Python, and Ubuntu to engineer all of that. The cost that you see here is CapEx. The OpEx cost and the man-hour cost would be different from that. To conclude, this service provides all of the users and students across the world a platform to enjoy the benefits of network simulation software, to dive deeper into complex network topologies rather than just playing with 2 or 3 routers, and all that without bearing the cost of the processing overhead that is associated with it. From the product owner perspective, it provides a university to increase its outreach to students and other network professionals across the world. The resources and the idle lab infrastructure when the university is not in session can be used for this service, and it would increase the efficiency overall. Also, if the project or the administrator needs collaboration from different users across the world, that is also provided from by our service as well. The future work would include exploring different network simulation softwares, incorporating different network nodes as released by the industry, enhancements in terms of security and IPv6 integration as well. And for organizations who do not have their in-house infrastructure, this entire code can be deployed on a commercial cloud to enjoy the benefits of the service. For any questions on a demo for our service, please find us outside after the presentations. Thank you very much.
All right, thank you, Team 2. Team 3, you can start walking up. So while Team 2, one of the big things they emphasized was the CPU reduction, which certainly was true. But one thing realized that they were making that service, you could host it, and now students could connect in remotely, right? So they didn't have to be in the lab to now use this complex network simulation software. They could connect in remotely. So that was a nice infrastructure outcome and benefit of that project. All right, so we got Team 3 coming up with low latency networking. Please take it away.
Thank you, Dr. Gifford. Hi everyone, I'm Jameen. My team's capstone is on low latency networking. My team includes Gaurav, Hona, Jom, and Rajiv. Our industry advisor is at Arista Networks Incorporated, and our academic advisors are Jose Santos and Dr. Gifford. The agenda of this presentation would be the purpose, the design, scope of this project, how we implemented this project, test overview, the results, and the takeaways for everyone from this project. The internet today comprises of a wide range of applications such as voice over IP, video traffic, video and storage, compute resources, etc. There are also applications such as high frequency trading applications which carry time sensitive data. So millions and millions of dollars are on the line for every millisecond. So low latency networking is a really important field of study in data communications. So the primary aim of our capstone is to study the behavior of end-to-end latency under different network scenarios and under the use of different device features. So in our testing, we have incorporated quality of service features and an SDN controller, and we estimate the inter-device delay and the intra-device delay. This diagram gives a basic overview of our test setup. The ISP cloud in here are the Arista switches that we use. The clients and servers are the endpoints of a traffic generator. We use Ixia as the traffic generator. It can generate different kinds of traffics, and it can generate multiple flows. Also, it provides with nanosecond latency measurement, which is really important for our testing because each nanosecond is important in this capstone. And our controller is a RU controller which uses OpenFlow as a southbound protocol. So we have different network scenarios such as congestion, using quality of service, generating different traffic flows. We make different combinations of these, and then we built a test suite after we build this test suite, we execute that test suite on 2 different Arista switches. The Arista switches that were loaned to us are 7050QX and 7280QR. The 7050QX is Arista's low latency focus switch, which has small buffers, and the 7280 switch is the ultra deep packet buffer switch, which has low packet loss, but again, the trade-off is that it has more latency.
Thank you, Jaimin. So to go over the project implementation, we implemented our project in 3 phases. Phase 0 involved setting up the controller, the traffic generator, and the network devices at their respective sites. Phase 1 involved running a series of test cases on the 2 network device families that were allotted to us, and Phase 2 involved doing a detailed analysis on the results that we obtained in Phase 1. To give an overview of Phase 0, we set up a controller at the Telecom lab at the university. We interconnected the controller with the network devices that were hosted on the Arista lab, and we also evaluated the variances generated by the XCR traffic generator. These are the test cases that we conducted in Phase 1. Case 1 and Case 2 involves 50 and 100% line rate traffic with no special features enabled on the network devices. Case 3, 4, and 5, we set separate traffic flows marked with DSCP values. This was done so that the different traffic flows could be prioritized. AF11, 12, and 13 are the markings, and AF11 marked traffic have the highest priority, with the priorities being reduced subsequently. However, in Case 3, we do not have any congestion induced. In Case 4, we induce congestion by sending 2% additional line rate traffic, but we do not enable any QoS settings on the network devices. In Case 5, we have both congestion induced, and also we enable the QoS settings on the network devices. Case 6 and Case 7 involve sending 50 and 100% line rate traffic using the flows that are installed with RU controller. And all of the test cases were done with both 1518 and 9214 byte packet sizes. For our testing, we opted for a linear topology because it gave us more granularity with respect to how the intra and inter-device latency could be measured, which was very important for us. The primary objective of Phase 2 was to do a detailed analysis that would answer these particular questions. The first question was whether the results that we observed in Phase 1 were in line with the expected performance results of the network devices, and if not, what were the reasons for those variances in measurements. We also included additional test cases to ensure that the values that we measured were accurate. Like I said, we had opted for a linear topology to measure the intra and inter-device latency. In the first linear equation, we account for 2 propagation inter-device delays and 1 intra-device delay. And in the second linear equation, we opt for 4 propagation inter-device delay and 3 intra-device delay. And these 2 equations give us accurate measurement with respect to what the individual intra and inter-device latency that is observed for the packet within the topology that we set up. For the test results, Jaimin will guide you through it. Rajiv, sorry.
Thanks, John. So in the test results, I'll be highlighting some of the important findings that we found out in our testing. So when we looked at the non-congestion scenarios, we see that there was the same expected behavior as we were expecting. So we got the expected results. When we looked at the controller scenarios, when we installed flows, we saw the latency was increased around 3% as compared to the normal lookup that was happening in the previous cases. Now, moving on to the interesting part, when we started inducing congestion with sending out tagged packets, without quality of service configuration done on the device, the expected behavior is that we have to see a random drops happening on the devices. That was observed on the low latency device. But however, when we looked at the high buffer devices, we see that the inherent preferential treatment was happening without any quality of service configuration done on the devices. And when we looked at the latency analysis, one interesting find that we observed here was that with the congestion and with quality of service being configured, the low latency device had an increase in latency of around 261% as compared to just 7.75% increase in the high buffer device. The inference that we were able to make from this was that the high buffer device was actually able to prioritize the packets and efficiently use these high buffers in order to give this effective latency results. Now we actually extrapolated these congestion scenarios to see how the devices reacted and if they actually maintained consistency as we increase the congestion rates. So here you actually see the graphs of loss percentages across different congestion rates for 2 product lines. On the left, you can see that's the low latency device. And here you see that as we increase the congestion rate, we see that all the 3 flows are being affected, and this loss is happening, it is increasing linearly. However, when we look at the high buffer device, we see that the top 2 flows are not facing any loss, but the least priority flow is actually suffering the loss. So this was one of the interesting finds that we were able to figure out. Now moving, and as the formula was being explained before, we were actually able to calculate the inter-device and intra-device values for the 2 different devices. And as you can see here, again, the high buffer device has a higher intra-device latency than compared to the low latency devices. Now to conclude, what we actually found out some interesting findings, and we were able to have an insightful discussions with our academic and industry advisors. As explained before, our main aim of the project was to study the end-to-end latency based on the different factors enabling and disabling, and on 2 different platforms. And it was a very good learning curve for us. And we were fortunate enough to have industry-grade equipment supplied to us. And if you have any more questions and want to know more about our project, please feel free to come at our booth. Thank you.
Okay, thank you, Team 3 in low latency. Team 4, please, okay, you're coming up. Let me pop this open for you. All right, Team 4 was software-defined voice over IP.
So we have implemented a software-defined voice over IP solution. On behalf of my teammates Nagendra, Nelson, and Simran, I would like to thank Dr. Kevin Gifford, Dr. Levi, and Rahil for their expert guidance, and Mr. Nick Chandler for pitching in whenever we had problems. Basically, we set out for this project because it was right now the industry has a lot of vendor proprietary solutions, and they cost a lot of money, inexpensive, and you have to go back and forth with the vendors to get fixes. So we set out to achieve this vendor proprietary solution, which was inexpensive, easy to deploy, and this deployed intelligence at the user end, which I will talk about more coming up. So the objectives we set out to achieve were having a centralized view of the network at the controller and knowing the entire data plane, and containerizing the VoIP soft phone and the open flow switch, which we used OVS for that at the user end, into a single package so that we could push flows over there, and implementing dynamic quality of service throughout the network so that we could have good call quality and reliability. So this is our functional block diagram. It's classic SDN. On the top layer, we have the application layer, middle we have the control plane, and the data plane. So our application interfaces with the controller and pushes flows on the data plane. And going into the specific messages that we had to see, we had to understand for VoIP, the call registration, confirmation of the registration, and then call initiation messages. So all of that is being handled by the application running on the top layer. And we provide a REST API for the users to interface with the application to get data about the ongoing flows and the calls. So there are 2 critical project elements. The first one is developing a custom PBX application with SDN capabilities at the controller, which would interface with the controller and talk to the data plane. And the second project element is containerization at the edge, where we would containerize the soft phone and the open flow switch. So going deeper into the project elements, we have to implement the traditional functionality. For the controller, we chose Ryu because of it's easy to develop stuff on Ryu and understand the SIP and RTP messages. So this was a very exciting challenge for us. And understanding Qos and how to implement Qos so that we could have best call reliability and dynamic path identification module. So we need to know about our entire data plane at the application. About the containerization, we had to we had some issues with having the containers talk to each other and talking to the controller, so that was an exciting challenge. And ensuring that Qos is deployed end-to-end between two users. So we have 3 phases in this project. The first one is placing a VoIP call itself. The second is containerization, and third is quality of service. So when placing a VoIP call, our controller has to understand the SIP messages and RTP messages, and basically establish the call between 2 end users. That's our test. That's what our test bed looks like. We have the application interfacing with the RU controller, and on the bottom left and the bottom right are the 2 end hosts where we have the phone and the OpenFlow switch containerized and interfacing with the data plane, and through that to the controller. Second phase is containerization. So here we had to containerize the soft phone and the OpenFlow switch that you see on the bottom left at the user end. And we had to make communication work between the OpenFlow switch and the controller. And third phase is quality of service. In this, we had to discover the entire topology. For that, we developed a protocol from scratch which would measure the latency between any 2 data plane devices, the OpenFlow switches. So we have a link state database at the controller, and we run Dijkstra on that entire link state database to identify which would be the least latency path end to end. And if we have enough bandwidth on that path, we would deploy flows so that RTP messages can flow between the 2 devices. And in scaling, we had to see how much our project could scale. We could scale it up to 15 OpenFlow switches and multiple users at the edge. And for the future work, we figured that if there is a link failure or a node failure, it takes some time for the topology to converge. And during that time, the traffic can get black holed, and future work can look at that and improve on the solution. And features can be created for things like conference calling, call blocking, the state-of-the-art VoIP features that can be added. And adding security at the edge. Since we have the OpenFlow switch containerized at the user end, we can push flows, block traffic, and do all sorts of amazing stuff at the user end. And the last one is self-healing. So if there is a link failure, we can initiate calls to the network administrator and get inputs on how to fix the network. Thank you.
All right, thank you for that nice summary on software-defined VoIP. All right, Team 5, please start ambling up here. Oh, yeah, Team 5 is next. All right, take it away.
Hi everyone, thank you for having us here today. My name is Srinidhi, and I'm presenting on behalf of our team and my teammates Mansi, Shika, Vaishali, and Yogisai. And our project is titled SDN-driven Voice-Assisted Intent-Based Self-Healing Network Framework, or simply put, VoiceNet. Over the last 2 decades, the internet penetration has grown exponentially with an increase in number of users and applications. As networks become larger and more complex, managing them becomes just as hard as well. Although automation has eased network configuration, the tasks of network administration and troubleshooting are still challenging because a lot of it involves manual effort. Because business interests don't directly translate into automated configuration, it requires a level of intuition to perform these tasks. So therefore, network administrators have had to collect network information, analyze it, then keeping business interests in mind and using their rationality and past experiences, they've had to go about carrying out these tasks. And because they're trying to find out what to do with the network, how to do it, and when to do it, it's a lot of work, and doing it manually does not scale. It is error prone, and it's time consuming. So therefore, what we're trying to do is trying to find a better way to perform these tasks. And we propose for a framework called VoiceNet framework, where the idea is that the network administrator only tells the system what to do, and the system is going to use this intent to try and find out how best to do it. And the idea is, since the tasks that were being performed by network administrators have now been delegated to software, from the point of view of the network administrator, their job is easier. And because of the nature of software, it is possible to perform these tasks at a larger scale in a more efficient way and in a faster amount of time, which is what we're going for. Like I mentioned, the concept of an intent is the network administrator tells the system what to do, and the system determines how best to do it given a set of conditions. Which is a good start. But even here, the challenge is to try and take an intent and to individually apply it to a large set of boxes across the network is challenging. It's not a very efficient way of doing it. This is where software-defined networking, or SDN, comes into play, where the concept of SDN is to treat the network as one single entity as opposed to a set of individual independent boxes. Because the SDN views the whole network as one entity, it provides a more global visibility of network events, and it provides a central point of control for us to push network policies. And that's why intent-based networking and SDN are two critical design elements for our project. And this was our system setup. We have a virtualized SDN topology, which was hosted on an ESXi hypervisor. And to manage the virtual machines, we use the VMware vSphere environment. We use the open source Ryu as our SDN controller, on which we develop Python-based applications. We'll talk a little bit more about the Python-based applications in the upcoming slides. We used Amazon Alexa as the voice interface, the voice assistant, where the user can interact with our system by issuing voice intents to Alexa. We developed 4 applications to perform different network management and troubleshooting tasks. The first one is Topology Discovery. Typically, gathering information, network-wide information, is challenging because there's no centralized view of the network, and because of vendor-related dependencies, this task becomes harder. So the question we're asking here is, can VoiceNet make it easier to gather network information? So here, the flow is that the network administrator will talk to Alexa by issuing an intent such as, Alexa, show me the topology. And this will be processed by our system, which will invoke the Topology Discovery script. Now, with SDN, the SDN controller talks OpenFlow with our network infrastructure, and at all times has a real-time global view of our network. So when this application is invoked, it coordinates with the controller, uses this topology and renders it in a visual format for the network administrator. The result here is the network administrator is able to gather information faster and in an easier manner, and this is real-time dynamic information. Regardless of what the underlying infrastructure is, as long as it can talk OpenFlow, we're able to map the real-time information dynamically, and that's the important result here. Now again, network troubleshooting is hard, especially in a large network. Trying to isolate network faults is harder, and it takes a lot of time to be able to resolve network issues. So the concept here is the network administrator will just tell the system, Alexa, detect and resolve network issues, and we're hoping that the system itself can try and resolve it by itself. The flow is the same here as well. In this case, when the voice intent is issues, it is processed, and the self-healing script is invoked. In this case, the self-healing application, rather, looks for misconfigurations in the network relating to OpenFlow and the BGP that is running on the network. It will compare it with a network source of truth file, which is the golden configuration or the proper working configuration. It will use that as a reference to roll back to a proper working configuration and then resolve network issues. It will then report to the network administrator that so-and-so issues were detected and resolved. So this is great when the application works as expected and resolves network issues, but it's important to realize that even when this application cannot fully resolve network issues, it can resolve some issues. It's automating some steps, which means it's reducing time for the network administrator from having to do them all manually. And the third application we developed was Qos Management Application. Typically, Qos is configured statically across all networks. What we're trying to answer here is, using VoiceNet, can we do it dynamically and in real time? So the Qos Management Application runs at all times. It monitors all the queues configured across our network and all the switch ports. Whenever it starts to notice packet drops on a switch port, which is associated with a particular queue, it is assuming that the packet drops are due to congestion, and then it is dynamically recalibrating and adding more network resources such as bandwidth to that queue. So, and as you can see in the screenshot as well, if you can make out, we're seeing transmission errors. And when transmission errors exceed a certain threshold, which is set by the network administrator via the intent, whenever this threshold is exceeded, the queue is reconfigured with more resources. So the result is that QoS is happening dynamically, in real time, and across the network. And that's the benefit of this application. And the final application is we've talked a lot about the advantages of a centralized point of control, but it's also important to realize that a logically central point of control can be a security vulnerability. So we developed an SDN security application that can protect the controller from denial of service attacks. In this case, we're looking for a specific type of denial of service attack, which is the open flow packet and flood attack to the controller. This application runs continuously and monitors traffic to look for the DOS attack on the controller. Whenever it detects the traffic to be an attack, it puts a firewall rule to block the malicious traffic, thereby protecting the controller and, in effect, the network. In conclusion, we saw that the framework was used to develop different networking applications that offered advantages. The common pattern that we saw was that we were using intent-based networking. It was easier to perform tasks. Using SDN, it was possible to do these tasks in real time across the whole network. So more applications can be developed based on how the network is more relevant to the network using the same framework, and be assured that we obtain these advantages. In the future, we can use the concepts of machine learning as well to build better models that can more efficiently analyze traffic patterns and decide to act later on. It was a good learning experience working on this project. We were fortunate to have to be under the guidance of amazing people like our academic advisor, Dr. Levi Perigo, our course instructor, Dr. Kevin Gifford, and our industry advisors from Facebook, Brandon Premo and Bettina Glusman. So we're thankful for them. We're also thankful for the department for providing this opportunity for us to present our work. Come by our table to learn more about our project and fortunately see a demo as well. Thank you so much. It's been a pleasure talking to you today. Thanks.
All right, very nice job. All right, so next up we've got Team 6. Team 6 was one of our sponsored projects from the Aerospace Corp. You know, ITP rebranded as TCP, and certainly cybersecurity is a big problem for everybody, including for spacecraft. And that's where I'm going to hand over and let this project start from. Josh, it's all yours.
Hi, everybody. Speaking on behalf of Team 6, along with my good friend Alex over here. My name is Josh. If you come say hi to us later at our table right outside, you'll meet my teammates, Ryan, Abdullah, Hassan, Scott, and Don. Our project was involving spacecraft cyber anomaly threat detection, deterrence, and reconnaissance, codenamed Scatter. Here is a brief presentation roadmap, but we'll go ahead and jump right in. For decades, spacecraft systems have been designed to be resilient and durable, to be launched into space and left alone with very little maintenance for years. And while the architectures and protocols used commonly for decades now will help protect against threats like solar flares and radiation, they are not prepared for malicious cyber attacks that they might face today. And that is what our project was aiming to change. We wanted to prepare satellites with an onboard security monitor that can in real time detect, deter, assess, and potentially mitigate attacks as they happen. To accomplish this, we identified three main goals that we had to achieve. First and foremost, we need an environment to work in. We need a satellite that we can test on, and unless we can find a net long enough to catch one in the wild, we had to make one ourselves. This was actually more difficult than it appeared it would be at first, because a lot of the protocols in place and the architectures that I mentioned before that are decades old, like the MIL standard I'll talk about later, has gone largely, MIL standard 1553 has gone largely unchanged since the 90s, and while there is a, I believe, 500-page document explaining the protocol and the standard for it, there's no open source implementation for it. So we could not gain insight into that protocol, and we had to build a lot of things ourselves from scratch. The second thing we had to do was assess the threat space that a satellite might face and the attacks and the attack vectors that are exposed in the wild as the satellites are in orbit. This is a relatively new area of research, and there's not a lot of information out there, and a couple of the researchers currently working on this that we contacted could not disclose anything to us because it's all naturally very confidential. So there's no tools out there for satellite exploitation. There's no pre-built Nmap or Metasploit module for attacking a satellite, so we had to figure out what those attacks might look like so that we can ultimately achieve our third goal of detecting and assessing attacks as they happen with our onboard security monitoring tool. This also provided a couple challenges that were pretty unique, such as the monitoring tool had to be on the satellite, but it had to be functionally separate so that we could ensure it was safe, so that if the flight computer or any other part of the satellite was ever compromised, we could make sure that our security monitor was not compromised as well. And I'll break that down a little bit more in a moment here. But first, we had to get a satellite to work in. What does that mean? What did we decide to do? We decided to emulate a CubeSat using the military standard 1553 bus was our goal, and it would have some primary subcomponents of a flight computer, remote terminals that would represent tools that you would have on a satellite, like the star tracker, the thrusters. Those would all be represented as remote terminals on the bus communicating with the main flight computer. We had to make sure the flight computer was a real-time operating system and make sure it was as closely representative of an actual satellite as it would be in space as it could possibly be. And we thank a lot of our work on that effort to the Aerospace Corporation, who provided constant feedback all the way through as we developed our design. And our design we decided with was we used a Zinc ZC706 FPGA from Xilinx, which is a FPGA that is commonly used in satellites today. The main reason we decided to use it is FPGAs have configurable hardware. The one that we have has 2 ARM cores, which were the main processors for our flight computer, but we could also configure what they called soft processors in the rest of the fabric of the FPGA. So we could spin up and define the hardware for these soft processors any way we like to enable that hardware separation that we needed to ensure the security monitor was kept safe and separate in the case that the flight computer was ever exploited. We also used it to spin up several remote terminals to represent other components of the satellite. To give you a broader view, this is our concept operation diagram. Typical satellite communications are initiated from mission control on the ground. They fly over the wire on the ground to a ground station, which transmits them up into the air to the satellite. The main focus for our project here was on board that flight vehicle, where the computer, the flight computer, and the remote terminals all sat and talked with each other. Here you'll see our main processing system would be our flight computer. It needed a real-time operating system. It would have flight software running on it to act as a command and control for the whole satellite subsystem. It would need to be hardware separated from the microblaze, which is the soft processor that would be our security monitor, which needed a method to gain insight into the flight computer without the flight computer being able to see back into it or manipulate its state. And communications would happen over the MIL standard 1553 bus, and both the bus and the processing system were our vectors for attack that we explored. We looked into ways that the processing system might be potentially exploited with rootkits, with side channel attacks, with buffer overflows, and we looked into ways that the bus communications themselves could be attacked by remote terminals spoofing communications from another terminal, by injecting data into commands as they were happening live, by denying spectrum or any sort of bandwidth whatsoever over the bus. And that's conceptually how everything looked. This is how our implementation looked. If you go and visit our table, Team 6, we're right outside, you'll be able to see the Vivado block design that implements, in essence, this. The Zinc programmable logic was our processing system. It hosted our flight computer, and the processing system was our flight computer, and the programmable logic was the soft processors that were our security monitor and our remote terminals. And there's a picture of our FPGA board to accomplish our internal subsystem communications. In our model, we were not able to implement the MIL standard 1553 for subsystem communications. We use a shared BRAM interface instead. but we were able to create a standalone MIL standard 1553 data layer emulator. So now we'll loop back to why the MIL standard was so hard to deploy. It has very specific voltage requirements. It has a data and physical layer component. There were numerous command words that we would have to implement, but we identified with Aerospace Corporation and Kevin a subset of the commands to implement in the standalone emulator to really just explore how the data layer communications would happen with, you can see our example of the packet structure there with the command word, status word, and data word for communications between the controller, which is our flight computer, and a remote terminal. And we were able to emulate these separately in order to assess how the MIL standard might potentially be attacked. And now I'll pass things over to Alex to tell you guys the results.
So as you could tell, the scope of this project was quite large. How much of it did we actually get through? Well, we actually, we built this test bed, and we got the whole thing more or less working. We have a flight computer and then a security monitor running simultaneously on different chips on the same board in such a way that the security monitor can look into the memory of the flight computer, but not the other way around. We also have, as I was mentioning, a separate standalone implementation of the MIL standard 1553, which is going to be the communication, as well as these remote terminals. So at the moment, the testbed kind of looks like satellite, it acts like satellite, but it's still working on talking like satellite. It is, however, enough to actually do some preliminary research into the threats that one of these satellites faces. We've found that there's a bunch of onboard vulnerabilities that could be exploited if someone in the supply chain were to insert something into the satellite as it's being constructed. They could actually exploit quite a few things when the satellite finally gets into the air. There are certainly other things that could be taken on. So, for example, being able to attack the satellite remotely from the ground. We still have yet to figure that one out, but that can be left for future researchers. The threat monitor was the most experimental because we weren't even sure if this would be possible, but we did manage to get the threat monitor to sit on the same board as the flight computer and read its memory in a one-way fashion. We were even able to find certain fingerprints in the entire memory of the flight computer that would tell us what the flight computer is doing and how it is behaving, and potentially find if it is acting in an anomalous fashion. Of course, there's a lot that we would hope to get. We're hoping to provide some kind of safe reset capability and stuff like that, but that was scoped out just for time reasons. So overall, we did actually make an unclassified open source testbed for people to actually try out some of these attacks on as close to a satellite as you'll get before you go up a few thousand feet. We were able to then use this to perform initial research and even show that a security monitor is a viable option, show a proof of concept that actually is currently working. The nice part about this project, it is very forward-facing. There's a lot of room for improvement and for future research to be done. So a little of this might actually be just tuning it, making it look more like a real satellite and actually getting this communication working. But the majority of it would be actually now doing this research on whether or not these attack vectors are possible, whether or not, so we've looked into onboard attacks, but there's certainly a host of other things that people could try, so attacking it remotely from the planet Earth, compromising remote terminals, hitting it with a hammer, there's a bunch of stuff that you might be able to try out. If you are interested in any of this, please come by our desk. We're just going to be out there. We can show you a live demo and talk about the things that we have gotten working so far. That is all. Thank you very much.
All right, thank you, Alex and Josh and Team 6. And again, special thanks to Aerospace Corp. They were fantastic mentors as they sponsored that project. All right, next up we have digital privacy and some of its concerns with Team 7.
Awesome. Good evening, everyone. My name is Archit Mathur, and I'm here with Richa Keswani. Both of us, along with Aditya Kelkar and Kanchi Chitalia, worked with Dr. David Reed and Dr. Kevin Gifford on our capstone project, which is Growing Debate on Digital Privacy, an update on web tracking and user concern. In today's presentation, we will begin with a brief introduction of our project and the underlying problem statement. We will then move on and talk about a few steps that we did for the completion of this project and some critical elements of our project. After that, we will present you with some data that we have collected along the process and the results that we got from the analysis of that data. And at the end, we will conclude with some future work that could go on into this project and make it even better. Web tracking and digital privacy have been huge topics of debate lately, and our project aims at understanding this landscape a little better. Our project can be divided into two parts. The first part is understanding the extent of web tracking that is happening over the internet. We do this by counting the number of web cookies present on different websites. Cookies are basically small files that hold information about you when you are surfing on a website. These files can either be stored locally on your browser or can be sent back to the organization that created it. The second part of our project was understanding the perception and concern that users have regarding web privacy and web tracking. For us to achieve this, we conducted a survey on campus, and the results and analysis of the response that we got helped us understand the user's perception and concern. In this slide over here, we're talking about the various steps that we took to complete our research. We started out with gathering data about the number of trackers that are present on different websites. For this, we use tools like OpenWPM and Ghostry. These tools crawl onto different websites for us and gives us the amount of first-party or third-party trackers that it was able to identify on those websites. After we had enough data about the number of trackers present on different websites, we used this data to create some statistics. These statistics help us get a better understanding of the current state of web tracking. This data also helped us in the next part of the project, which was creating questions for our survey. The survey was one of the most important parts of our project. And for us to be able to conduct a survey on campus, we required an approval from the Institutional Review Board. After we had that approval, we were good to go, and we distributed the survey to students in ITP, TCP department, and the response that we got from it were useful in creating our final analysis report. These are the 21 websites that we selected for our analysis. We chose these websites based on their general popularity in the United States and their specific popularity among the audience that we are targeting. While searching for websites, we divided our search into 4 categories, that is e-commerce, finance, news, and social media. We did so that we can get a holistic view of an average user's daily interaction with the internet. After having completed the entire data collection process, we got some really interesting results that we'll share with you right now. This pie chart over here talks about the number of third-party trackers present per page load. And as you can see, that more than 50% of the websites that we had analyzed had more than 15 third-party trackers on them. And this number goes as high as 70 third-party trackers on a few of the websites. The second graph over here talks about the prevalence of third-party trackers on different categories of website. Over here, you can see that third-party trackers are most prevalent on news and blog websites, whereas they're least prevalent on social media. This was a really interesting finding, as we learned that websites like social media websites like Facebook and YouTube don't always allow a lot of other organizations to plant their trackers on their website, but they themselves have a lot of trackers planted on other websites so that they can get information about the users from varied sources. The third graph over here talks about the prevalence of websites by the organizations that own them. Over here, you can clearly see that Google tops this list by a huge variation. In our analysis, we could see that Google and services owned by Google, like DoubleClick and Google Analytics, had their trackers present on 85% of the websites that we had tracked. All these results help us get a better understanding of the current state of web tracking. And now Richa will talk about our survey and the results that we obtained from the survey.
Thank you, Archit. So I'll be starting with a brief overview of our survey. We created our survey on SurveyMonkey, and it comprised of total 15 questions. There was just one question asking about the education level of the participants, and all the other questions focused on our research. Our questions were designed to focus on 4 categories as mentioned here. We also gave a brief description of our survey on the first page and described what first-party tracking and third-party tracking meant, each with an example, because we didn't expect all the audience taking the survey to be familiar with these terms. We also listed the sites that were used for our tracking measurement on the first page itself. As of now, we have received a total of 45 responses from the students of the TCP/ITP department. Now moving on to the survey results. Since the survey respondents were basically from TCP/ITP background, having a strong technical knowledge, most of the participants felt fairly confident about their knowledge of web tracking technologies. Then here we present to you the awareness and concern levels that students have regarding the first-party tracking and third-party tracking. The awareness levels were much higher for first-party tracking, while the concern levels were higher for third-party tracking. The higher concern for third-party tracking made sense to us because the users are not directly interacting with any of these third-party services and are sometimes not even aware of their presence. Then we also asked participants about their comfort level with the behavior of websites for tracking their online behavior for the purpose of targeted advertising, both before and after we presented them with our tracking measurement results. So most of the participants expressed their discomfort with this behavior of websites and were also more inclined to use additional privacy tools to protect their privacy online. So we chose this topic as our capstone because this has been in the limelight for quite some time now and has become more user-sensitive recently. The increasing number of third-party trackers on the websites is a concern for all of us and would become even more concerning if these third-party services go on and track our PII. This project overall helped us get a better understanding of how web tracking works and understand different web tracking technologies. So for the audience with a strong technical background, we did see quite a few differences between their awareness and concern levels for both kind of trackings. We expect that the results would vary even more for an audience with a diverse background. Also, most of the respondents did take minimum efforts to maintain their privacy online by using one or the other privacy protection tool, but only a few went a step further and read the privacy policies or deleted their cache regularly. For our future work, we would be interested in including more websites for our tracking measurement results to get a holistic idea of tracking across the web. We would also like to expand the audience for our survey by including people from different age groups and different backgrounds. We would also be interested in analyzing the efficiency of commonly used privacy protection tools and see if they're doing what they actually claim to do. And based on the results, we might find it relevant to include a couple more questions in our survey. That's it from our end, and we hope to see you during the booster session. Thank you.
All right, thank you, Team 7 and digital privacy on websites. So while Team 7 was trying to inform you about third-party cookies, our next team, Team 8, wants to snort all the data out of the air, scan all the frequencies from Bluetooth to Wi-Fi to LTE, and slurp your traffic. So they're looking to show you how to do this dynamically. Abhishek.
Good afternoon, everyone. We are Team 8. My name is Abhishek. I'm joined with Vaibhav, and if you visit at our poster, we are joined with two other members, Akhilesh and Ankita. So let's get right into it. So our project is the scanning of the RF spectrum using a software-defined radio. So this is the basic overview. Let's get right into it. So as of now, if you look into the market, Cisco states that as of 2030, there are going to be 500 billion connected devices on the network. So it means that the number of wireless devices are going to increase exponentially, which are going to use the RF spectrum. So the scanning of the RF spectrum is going to become one of the most important elements in a wireless engineer's domain. So the field of application which it states here is that we wanted to come up with something which is low cost, and it integrates all the different bands like Wi-Fi, Bluetooth, and LTE. How many times have we pulled our hair when a Wi-Fi is not working or any other internet is not working, right? So we know that sometimes the RF spectrum is not utilized efficiently. So our solution also integrates some kind of analytics which the user can utilize to understand how the network is working. And one of the most important things which we, in this project we have achieved is that we have integrated all the 3 different technologies of Wi-Fi, Bluetooth, and LTE into a single system. So just a click of a button will give you the different scans of all the 3 different technologies. So that's the problem which we have addressed, and the potential impact is that there are different vendor solutions in the market, but they are very expensive or they are very highly selective in their implementation. So we have implemented a low-cost solution which you're going to see in the next slides. And also we are also giving them analytics for the user to understand how the RF spectrum is deployed. So basically, this is just a snapshot of how our project works. So if you go into a coffee shop like Starbucks, this is the RF environment which you're going to see. There are a lot of stations, and there's obviously LTE network in the environment. There are a lot of access points in the environment. There'll be printers, and there's a backhaul network with switch and wireless LAN controllers. So if you can see, we have just stuck the software-defined radio between the coverage areas of all the 3 different technologies, which are going to scan or which are going to snort all the packets and then send it to a terminal or a command station where we are going to run our algorithms which will decide how much of the spectrum is utilized and what is the good solution for you to go ahead. So this is the basic levels of success. We divided the project into different solutions. So first we wanted to just concentrate on the unlicensed band, that is Wi-Fi and Bluetooth, and then go into the licensed spectrum of LTE. So this is just basic division of work which we have done. So if you can see, this is just the basic system which we have implemented. This looks very simple, and this is the software-defined radio which you're talking about. This is made by Etis Research. It is a USRP B210 with a rubber ducky antenna. So this is the terminal or the laptop which we're talking about, where we'll see all the different results which is going to be generated for the user, and also the GUI. And this is another software-defined radio called HackRF1. So basically, we deploy this system in any wireless network, and then we capture all the software-defined radio captures all the different packets, and the analysis is done by the code which is running in the terminal. So I'm going to hand over the mic to Weber, who is going to explain about the different results and the different analytics which we have done. So over to you, Weber.
Thank you, Abhishek. So moving on to the results, so we have divided the testing into the 2 parts. First is like control testing and the uncontrolled testing. So we'll start off with the Wi-Fi. So in the control testing, we can see we took like one access point with a known SSID and BSSID. So test underscore AP was our known SSID and the BSSID, and we scanned with our SDR scanner and tried to see whether we are getting the same what we have configured previously. And then we also got some hex dumps to see like whether we are capturing the live data or not. And along with that, we have some 2.4 and 5 gigahertz Wi-Fi information, like the channels, the frequency of operation, the number of packets that we have captured, the count of the management frames. After this, we'll take a look at the uncontrolled Wi-Fi testing. So this is the capture we took in like DLC lobby, where we got like so many SSIDs and BSSIDs, and the same information which we saw in the previous slide. Just wanted to scan in an open environment, in an uncontrolled environment. And this is the actual results that we wanted to show for our project. So we can see like 3 options, and a user can select any one of these technologies to scan and see the results for. And for Wi-Fi, we can see the same thing, like different channel numbers, center frequencies, bandwidth. So mostly we are scanning like 20, 40, and 80 megahertz channels. In 802.11 AC, we can go for like 80 megahertz plus 80 megahertz or 160 megahertz, but our SDRs were not capable of supporting that, so we just stick with 20, 40, and 80 megahertz. Then we can see the beacon count, the different management frames flowing through the channel, because we know like a lot of Wi-Fi performance is taken down by the management frames. So we need to take this into account. And then again, the BSSIDs and SSIDs, which we scan on those particular channels. So this is the percent utilization chart for the Wi-Fi. So we can see the channels 1, 6, and 11 in 2.4 got occupied, and then a couple of other channels in the 5 gigahertz. So this, moving on to the Bluetooth now. So this is just a raw packet capture that we got for the Bluetooth. So Bluetooth is basically having an access address and an advertising address. So advertising address is basically the MAC address of the device, which is transmitting using the Bluetooth technology. And access address is something when Bluetooth device establishes a link with other Bluetooth device, so it gets an access address. And in order to scan the data on that particular channel, we need that access address. So right now what we are doing is we are scanning only on the advertisement channels, which are channel 37, 38, and 39. Because in order to scan on the data channels, we need some license tools and we need some other permissions for that. So because of lack of these things, we just scan only the advertisement channels, 37, 39, 38, and 39. This is the actual GUI, the output for our project when we scanned the Bluetooth, where we can see the channel center frequency, bandwidth, the advertisement addresses, and the access addresses. So basically, access addresses are fixed or constant for the advertisement channels, and that's why we are seeing the same data for all the 3 different channels. Now, moving on to the LTE. So for LTE, we are getting the duplex mode, the cell ID, the transmit antennas. So it's basically telling how many transmitting antennas the eNode B is using. Then it's telling the center frequency and the received power. So when we start scanning the channels like simultaneously or continuously, the RSRP or the received power is going to vary based on that particular power received on that particular time instant. And then we have the resource blocks. So these are the 2 frequencies we scanned. One is for the AT&T and the other is for the Verizon. So based on the resource block, we can calculate the bandwidth because we know like every resource block is having 12 subcarriers and each subcarrier is like 15 kilohertz wide. And when we consider the guard intervals along with that, then we can calculate the channel bandwidth from that one. And just for the references, so how we verified whether our LTE test results were working or not. So these are some snapshots from the Android and the iOS. So you can use like any Android applications. There are thousands of applications available which will show the live statistics for the LTE, and the same is available for the iOS. So we verified the same things like what cell IDs we were getting, how many transmitting antennas were there, the RSRP and the RSRQ. All these details we verified with what our SDR was capturing. And moving on to the last part, like the conclusion and the future work. So conclusion is instead of spending thousands of dollars, SDRs are like the cheapest option available and with which we can scan all the different technologies, all the frequencies. And the future work for this project is more powerful SDRs can be used. So the SDRs which we are using right now are the USRP B210s and the HackRF1. So they have bandwidth up to 80 megahertz. So we can use more powerful SDRs with wider bandwidth. Maybe we can go for like 160 megahertz in the future. And right now we are using only one SDR for scanning one channel at one particular time. So we can use like powerful SDRs having 3 different RF modules, and we can scan all the 3 different technologies at once. So if we do that, then the cost will be reduced further. And when we think of doing that one, like scanning all the 3 different technologies with one SDR, so there will be like a huge interference between the different transmitting antennas and receiving antennas. So we'll have to mitigate that one, and that factor we need to take into consideration. And maybe we'll have to implement the things like the different diversity mechanisms, the transmit diversity and the receive diversity. And yeah, that's all. Thank you. And please do visit for further clarification and explanation. Thank you.
All right, thank you, Team 8. How to cheaply scan the spectrum and see what's going on. All right, next up, we got Team 9, which is one of our sponsored projects from Equinix. So thanks again to Equinix and Brooke, who is here, and we'll let Team 9 start off with their results.
Thank you, Dr. Gifford. Hello, good afternoon, everyone. My name is Sarang, and the project of my team is SDN NFV VNF service chaining. This project is sponsored by Equinix, and the team is here today. Let me start with the brief overview of the project. So what is service chain? Service chaining is the set of network functions linked together to support an application. And what is network function virtualization, or NFV? It is the decoupling of software from the traditional network devices so that that software can be deployed on a server as a virtualized infrastructure. So why service chaining with NFV? Because it has advantages like it's easy to provision, easy to reconfigure. It eliminates the need for network hardware devices, and also it it takes less time to deploy and therefore reduce capex and opex. The field of application is that service chaining using NFV facilitates dynamic network design, and it allows deployment of desired network functions on a server environment. And talking about why this project was built, in the literature survey, we did not come across any research study that evaluated the performance of servers when a service chain was deployed. Therefore, we in this project are focusing on the testing of operations of service chains to gather server performance and network parameters on the server and the chain. Also, this project is going to help industry professionals to predict how deployment of service chains and how different VNFs affect the server and the network performance. This is an operational diagram of the implementation of a project. We have used one server and two different hosts acting as IPOF client and IPOF server, as you can see in the diagram. We have used Ubuntu as the operating system on the server, and we have also hosted OpenStack, which will be hosting the service chain on the server itself. As you can see here, VNF 1, 2, and 3 form the service chain within the OpenStack environment between the two blue routers on the left and right. So when the traffic is passed through the interface on the left from IPOF client, the traffic goes to the virtual bridge, and we are using policy-based routing on the Ubuntu server to force the traffic inside the service chain. The traffic flows through VNF 1 through 3, and it goes to IPOF server, and it follows the exact reverse path to go back to the IPOF client. While the traffic is flowing through service chain, we are gathering performance metrics on the server and also on the VNFs, and we are storing them, doing analysis on that, and we are also representing that data on a virtual tool, on a visual tool. So this is the test procedure that we followed. First, we have gathered metrics when no service chain has been deployed on the server. So this basically gives us a baseline to study how service chains affect the server performance. The next step was to deploy and configure the service chain. This step was done manually. And after that, we built a Python application which automated a number of tests for us. The first test we did was to gather metrics on the server when the service chain was deployed but no traffic was passed through it. The test followed with a latency test, and we also collected metrics. The application also collected metrics for various kinds of traffic, like TCP traffic, one single TCP connection, a TCP stream connection, which means that we configured like 100 parallel connections from the IPOF client to the IPOF server to see how the system behaves, and we also checked metrics for UDP traffic. The metrics that were collected on the server were done using Prometheus and Node Exporter. We used Notchy, which is a built-in OpenStack monitoring tool, to gather the metrics for the VNFs which were deployed as service chains in OpenStack environment, and we used Grafana to visually display the metrics. These were the metrics we collected on the server. So we had 720 data points per test. Each test for all the three different points shown here went on for 1 hour. And for server, we had 720 data points. We collected stats for CPU utilization, memory utilization, and the CPU load for the server. For the service chain, we collected metrics like latency and throughput for various kinds of traffic. And we had, for service chain, we had data points per second for each test. And for the VNFs deployed in the service chain, we had 12 data points, and we collected metrics like CPU utilization and disk usage, among others. Here I'll be talking about the test cases that we conducted. We conducted 11 test cases, and the first 3 among them are a single NAT, a single router, and single firewall. Next, we moved on to do testing for a combination of 2 of these 3, and then a combination of all of them, firewall, router, and NAT, as you can see on number 8. And we also tested for a series of routers as well. On the right, you can see the components that we used. In the software part, we can see we have used the stable Rocky version of OpenStack. And the VNFs, we used a Juniper VSRX, which was used as firewall, a Cisco CSR device, which was primarily used as a router, and a VivaOS NAT device. Here, I'll be talking about the test results that we have gathered through all the testing we have done for the 11 service chains. I'll be only talking about 2 inferences of CPU utilization here. As you can see in the graph here, the CPU utilization increases with the increase in number of VNFs in the service chain. So first is N, NAT, router, firewall, and with a router and NAT, the CPU utilization goes up. Also, out of all the traffic types, for a particular service chain, maximum CPU utilization can be seen for a TCP stream connection, then the UDP traffic, and then TCP traffic. And also, we have collected, we have made more inferences about memory utilization, latency, throughput, CPU utilization on the VNFs apart from server. So I request you all to drop down to our booth to learn more about that. To conclude the presentation, the scope of our project is that it is going to help industry professionals to predict how VNFs behave on industry-grade equipment. We have created a test environment in our project where industry professionals could test VNFs that they would like to deploy in their production. Also, although in this project we have tested only 3 VNFs, the ones I showed in previous slides. This research can be further extended to accommodate and test VNFs from different vendors or open source VNFs. Also, replacing the networking component within OpenStack could be an option. It might give us different network results. And finally, we have used OpenStack as an orchestration tool here. We could use different orchestration tools to see how the system behaves by deploying those tools. That was my presentation. I'd like to thank Equinix team here. They've given a very good support to us. I'd like to thank the department, Dr. Perrier, Dr. Gifford, and thank you everyone. Have a nice evening.
All right, thank you, Team 9. So one thing that I may not have came across, but I happen to know, is they have a ton of data and test cases, and they ran enough tests that all their results are really statistically valid. So they did a really nice job on data collection and analysis. All right, next up, we got 2 more teams, gang. We got Team 10, and we're going to talk about SDN network orchestration.
Thank you.
Good afternoon, everyone. My name is Aishwarya Gaikwad. Karthik and I are here to represent the eNetApp team. My team members are Arun, Sanjana, Sanket, and Karthik. So the agenda for this presentation is as follows. I would be defining the problem that the enterprises are facing today and how our project is a solution to that problem. Then I would be walking you through the concept of operations that can give you a clear idea of what components our project has. Then again, I'll tell you our thought process in defining the level of success for this project. Design, solution, implementation, and the test results will be covered by Karthik. Today, enterprise networks have widely adopted the traditional architectures, and these traditional architectures are becoming more complex day by day because they offer minimum network-wide visibility. So software-defined networks came into existence. But again, we have here a problem, that is the universal applicability. It offers minimum universal applicability. And also we have very less number of employees that are well-defined, well-versed with the software-defined networks. So then what's the solution? eNetto app is the solution. eNetto app is the SDN Enterprise Orchestration Application. It is a all-in-one solution to scale, automate, abstract the configuration, and also that makes the network administration very, very easy. This, as you can see, this is the concept of operation diagram. The eNetto app uses a northbound protocol to feed the user input into the various components of the project. Then there is SSH-based automation tool that is used to configure the underlying network infrastructure. Then we have is the SDN controller. SDN controller is responsible for installing flows into the SDN-enabled devices. And then we have the containers. Containers are responsible for hosting the network services on the cloud. And the container management platform is used to manage all the containers. This is the slide of level of success. We have the first level of success is the deployment of network infrastructure. By network infrastructure, I mean is the traditional domain, SDN domain, and the services that are running on the cloud. Our second level of success is the integration of all these domains so that we have end-to-end reachability and accessibility to the services. Our third level of success is the validation of network oppression for configuration accuracy, scalability, resiliency, and accessibility. And our fourth is to implement the abstracted web portal so that the user has the functionalities to orchestrate the network. In design solution, as we know the components by now, for SDN controller, we have the Rio controller. For hypervisor is the KVM hypervisor. For cloud management, we have considered the OpenStack option. For container management platform, we have come up with Kubernetes. And for configuration management tool, it's a combination of Ansible and Python. Project implementation and the test results will be covered by Karthik.
Thank you, Aishwarya. So moving on to the project implementation. The project implementation consists of two layers of networks. So one would be the underlay network, and the other would be the overlay network. The underlay network consists of the OpenStack multi-node cloud, wherein the Rio controller, the TFTP server, the DHCP server, and the web servers are hosted as Docker containers. The underlay network consists of the SDN domain and the traditional domain interlinked with each other. So we use BGP as the routing protocol to facilitate inter-domain connectivity. So we have hosted our BGP speaker application on the Rio controller, which facilitates this interoperability. So once the BGP speaker application gets the routes from the traditional network, it installs the flow entries on the OVS switches present in the SDN network. Once we have end-to-end reachability of services, then we are tasked with automating the entire network through a one-touch provisioning system. So we have come up with an application called eNetto app, which is hosted on the cloud, which will enable to provision the entire network and orchestrate and validate the entire network. So this is the eNetto app dashboard. The image that you see on the left side is the web portal that is being presented once the user logs into the application. And the image on the right is the option that is being presented once the user clicks the configuration button. So further details can be revealed once if you can step in our table to understand more about this application. So going over the test plan overview, the test plan consisted of, we had a methodical test plan, and it consisted of unit tests, system test, integration test, and acceptance testing. So in unit testing, we focused on configuration and connectivity, and in system testing, we focused on multi-platform integration and protocol stability, because since BGP is involved and two disparate domains are getting connected, we need stability in BGP. And finally, in our acceptance testing, we ensure that end-to-end service reachability is possible. So finally, before delivering the product to the customer, we ensured we optimized all our scripts, and we kind of evaluated the efficiency of our application. So we conducted a study wherein the time taken for our application to configure the network of each domain and the time taken for manual effort to be configured on each domain, that is the average time taken for a human to configure each domain, was evaluated. These are the test results for the research study, wherein each domain was studied and it was evaluated. And initially, our automation scripts used sequential programming, wherein the scripts will be logging into each and every device sequentially. Then we optimize those scripts to incorporate parallel processing. So finally, then we integrated that with the eNet app so that the entire network is provisioned simultaneously. So the key takeaway from this slide is, when we orchestrate the entire network manually, as the number of devices increases, then the configuration time scales linearly. But our application uses parallel processing so that irrespective of the number of devices involved, it takes the same average time that is being displayed here. So the lessons learned. We worked closer to Agile methodology, and which enabled us to kind of categorize our tasks involved per week. And we had a Kanban board to schedule our tasks and sprints. And risk evaluation and a proper well-defined risk matrix helped us to evaluate the risks involved. We use CI/CD approach to minimize integration issues because disparate domains such as traditional SDN and cloud were involved. And finally, efficient model testing reduces such system integration. To conclude, our eNet app is a really good solution for enterprise networks which involve cloud, traditional, and SDN domains. It reduces human error, and it's a hybrid solution, and it promotes faster deployment. So the future scope of this application would be to incorporate self-healing capabilities, and you can also incorporate predictive analytics and artificial intelligence. And we can make the application improve on responsive monitoring of network health, and which can validate intuitively the network failures happening in the network. Thank you, and please head over to our station to have a live demo of the application.
Okay, thank you guys for all the presentation and for everybody's patience here. We got Team 11 that will be walking up here, and they're going to talk about IoT. I have just a comment here since we're ahead a couple minutes ahead of schedule, which is nice. So overall, Team 11 and Team 6, which did the Spacecraft Cybersecurity, their projects were a little bit different in that they built the test beds, right? It wasn't a particular product. They were building the test beds to allow future research. So this team is in a similar manner of building a framework that allows you to detect malicious IoT behavior. And honestly, that, I'm going to take 30 seconds and give them a plug. That's applicable to any enterprise, right? Whether you're Zayo, or whether you're Amazon, or whether you're CU Boulder, and you're worried about malicious IoT devices being on your network and potentially compromising it. So this is a very nice generalized solution, and I just wanted to point out the wide applicability of this particular project. Team 11.
Good afternoon, everyone. My name is Alex. I'll be speaking with Andreas about IoT classification. We're Team 11. So first things is more and more devices are coming online. By 2020, this number is expected to reach nearly 30 billion. And so while this brings a lot of convenience in the form of IoT devices, from cameras to smart light bulbs, it also represents an area of vulnerability. Essentially, each of these devices represents a vulnerability or an entry point into a network. And so many of these IoT devices are currently being built and sold without security in mind. As people try to sell cheaper devices, they don't take into account encryption. In smart light bulbs, for example, a lot of them have been shown to store passwords in SSIDs in clear text. And so from this perspective, we thought it would make sense to develop a framework to classify IoT devices, identify them, and then classify them on a network and differentiate them from non-IoT devices such as a laptop. And once we did that, our goal was to then classify them as benign, malicious, or potentially unknown. So in broad terms, as I just talked about, is we wanted to go onto any local area network, be able to find all the IoT devices, classify them as IoT, and then start assessing their behavior. and from there mitigate any potential risks that they bring. So there's 4 levels of success that we were trying to achieve. The first was actually more difficult than we thought, which was to create a definition of IoT. It's almost defined as you know it when you see it, or it's defined in the negative as in everything besides a server or a laptop. And so Andreas will talk a little bit about our testing results, but we found things like MAC address, really had no correlation, and we decided to look more at the flow and to set up basically a definition by capturing the components of the group to then create the definition of IoT. So we would first say these 4 or 5 devices that are included in the LAN, these are IoT, and then let the machine learning look at that, take some of the characteristics on its own and see if it can find any correlations. So that's the algorithm that we decided to try to work on in level 2. In level 3, our goal was to take this information from a local area network, not only in batches, but as close to real time as possible, considering that's how most network security, that's the most value that we would bring to a network security company or to even an academic environment. And the final level was to essentially develop the mitigation scheme to not only say, hey, here's an IoT device that may be acting irregularly, but what can we do about it? How can we automatically prevent that? So I'll hand it over to Andreas to talk about our ConOps.
Okay, so coming into this project, we had a little bit of a challenge when conceptualizing how we were going to get all this data managed. At first, we were anticipating to have full packets. This turned into NetFlow packets, and we ended up working with the CU campus OIT to facilitate the information from some of the subnets in the DLCs, so a building and campus. And we ended up coming with a cloud architecture using AWS to allow for scaling in case that this application or solution would be implemented somewhere else. So what we ended up coming up with was an S3 bucket to actually store the files themselves, then an EC2 instance to process the files. So we were originally getting the files in a .flow format, and we wanted to transfer these into CSV for easier management. So that's what we use the EC2 instance for. But I'm getting a little bit ahead of myself. So here in the ConOps, you guys can see the idea of the design was to create a black box that could be plugged into any router in a LAN and classify all the traffic going out of that LAN. And with that black box idea in mind, we came up with this black box design in AWS. So this is the S3 bucket that I mentioned. And then there's the EC2 instance at the bottom that would transform the data. And then the data itself would be stored in S3 in the proper format, in the format that we liked. And then finally, we would spin up an AWS SageMaker, which essentially is backed by an EC2 instance to easily classify the data, build our classification algorithm. Building this infrastructure or this flow allowed us to develop this test bed that Dr. Gifford mentioned earlier, where the algorithm itself is easily swappable. So if someone wants to try a different approach, they can just write a different algorithm within that SageMaker instance. But we've automated the deployment of this infrastructure with an infrastructure as code solution. So with this design solution that we proposed, we came up with a test plan with preliminary testing to identify different classifications, algorithms, and accuracy. Based on what Alex said, we ended up choosing the Amazon Linear Learner algorithm for our testing. It's a regression-based algorithm that relies on feature selection, like identifying the features, but it's a supervised learning algorithm. So we had to provide some training data before it could actually do anything. Then some intermediary testing to help fine-tune the parameters. And we used some Nest-connected cameras, smartwatches, smart speakers, et cetera. And then the final testing was to report on the success of the project or not. The test results were not quite what we hoped initially. We ended up not being able to classify as many devices as we wanted. We ended up testing in a small LAN, not the DLC initially. There were some other tests scheduled to be conducted, but there were some delays in setting up this pipeline so that those tests couldn't be carried out in time.
But we did see that the algorithm chosen wasn't as effective as we wanted. However, we did see some positive hits. And the other positive result of this project was that we actually achieved most of the success markers that we set out for ourselves. So in the first level of success, we wanted to define IoT. While we didn't come up with a list of IoT, we believe that the approach of classifying IoT as a predefined subset of devices is very adaptable for the enterprise environment or for an educational environment, because not every enterprise is going to have the same definition of acceptable risk. So creating this definition based off of a subgroup or a supervised learning algorithm would actually be very beneficial. And then we worked quite heavily with OIT to actually establish this connection on a 5-minute interval from their servers or their routers in the DLC LAN, sending the information up to our cloud infrastructure. Then in the second level of success, we did write that algorithm, but the accuracy is under question, and probably it wasn't the right algorithm for the specific subset of data that we used. And then this refining obviously could not take place because of this. And moving into the other levels of success, we did achieve level 3. We have an automated flow to get the data into the right format in the right spot at the right time. And then again, we didn't really get to suggesting mitigation schemes because of this. However, there were some interesting systems engineering tasks. We split the architecture into functional components, into data storage, processing, and classification itself. We found that AWS services lend themselves pretty well to this type of systems engineering approach. However, there was some subtleties with the AWS access control system where we originally tried to have multiple accounts interact with each other, and we figured out this is not a good approach moving forward, which takes me to the next slide. Some lessons learned. We're leaving this project with an infrastructure as code solution that deploys this environment into any single AWS account so that the algorithm themselves can be refined and tuned by either future teams or any organizations. Other than that, it was a great opportunity to just work with OIT and get a feel for the amount of data being processed in every single subnet of the CU campus. And thank you for all your attention. We're going to be outside if you guys have any questions.
All right, thanks, Team 11. All right, everybody, thank you so much for sitting through those presentations. The students really did a good job, and I'm typically a pretty hard critic. This particular group of 11 teams, really did a great job of engineering design and having some successful projects. So we're 7 minutes ahead of time. That's great. Everybody, thanks once again. Now, when you walk out, the poster sessions are all out there. And then I'm just going to point over here. There's a little room with food. So from 3 to 4 is essentially a networking hour. And if you have some time to visit some of the projects that were of interest to you, please stop by and chat with the students. And thanks, everyone. Much appreciated.